4.5. Some of you learned this in Algebra 2 and some of you didn't, so pay close attention. It's probably the hardest of the Chapter 4 sections, so this video may go a little long, but I'm going to attach the lecture slides in Schoology and Canvas in case you need to go back and review those. So the first thing we want to know is, what is a rational function? It is a function pretty much that looks like a fraction, and it's got a polynomial on top and a polynomial on bottom. So here's an example of a rational function. Consider f of x equals 1 over x plus 4. Find the domain and graph f. Well, we already know that for a domain restriction, we look in the denominator. So what would make this denominator 0? Negative 4 would make this denominator 0, so x cannot be equal to negative 4. So the way that we're going to write this in my math lab is with interval notation. Negative infinity to negative 4, union negative 4 to infinity. Now, how do you go about graphing it if you don't have a graphing calculator? Well, the exact same way that we have graphed every other function. We know that we have a vertical asymptote at x equals negative 4. What a vertical asymptote is, for those of you that may not remember, is a line that the graph approaches but never touches. That's an asymptote in general, but a vertical asymptote is just a vertical line that the graph approaches but never touches. And if you can see, this graph of 1 over x plus 4 approaches this but never touches it. Then you would just find values of x and make a table, like x and 1 over x plus 4. And you would just pick some points to the right of the asymptote and to the left of the asymptote. For instance, if we plugged in to the right of it, negative 3, we would get 1 over negative 3 plus 4 is 1. So 1. And we would plot the point negative 3, 1. And then you would just plug in a bunch of other points. We're going to do a more in-depth example later where we graph. So looking at these, there are a lot of examples in these 29 slides that we want to talk about the domain. Now, if you're looking at the graph, it's pretty easy to see, hey, we don't ever cross 0. So our vertical asymptote here would be x equals 0, and our domain would be negative infinity to 0. That should be a parentheses. Union 0 to infinity. I'm doing my best with the handwriting, guys. All right, so we have that. That's a 0 parentheses. If we look at our function, that makes sense, because what would make the denominator 0? Well, an x value of 0 would. Same thing here, and you can see how it's shown on the graph. A few more examples. Here, you're going to have to factor this denominator first, and I'm going to try typing it. That might look better. So when I factor this denominator, I have what multiplies to negative 2 and adds to positive 1. So x plus 2, x minus 1. So what would the zeros of that be? We would say x equals negative 2 and x equals 1, the opposites. But because they're in the denominator, x can't be negative 2 and x can't be negative 1. So we would have a vertical asymptote at negative 2 and a vertical asymptote at 1. I think I said negative 1, but I meant positive 1. All right, so we would write our domain. We would write our domain for this one. Negative infinity, I'm just going to write I and F, you'd write the symbol, comma negative 2, union negative 2 to 1, union 1 to infinity. And over here, it would be everything except what makes this denominator 0, which if you work this out and you write 2x minus 6 equals 0, you get 2x equals 6. So x equals 3. So everything except 3 is what we could have. So negative infinity to 3, union 3 to infinity. Here, we would do the same kind of stuff. I just left this slide in here so that you could see the graphs. Graphs of rational functions can have all kinds of funky shapes, but usually they're going to have more than one part. Because of these asymptotes, they're going to be broken up into different sections. Now, a vertical asymptote is found by finding the zeros of the denominator, at least the zeros for the factors that don't cancel out in the numerator and the denominator. If I were you, for vertical asymptote in my notes, I would write what makes the denominator equal 0. So it's going to be x equals whatever makes the denominator 0. Maybe we should write it like that. X equals whatever makes the denominator 0. If there was something that would cancel out in numerator and denominator, you would cancel that out first and then see what makes the denominator 0. So let's look at this example right here. Determine the vertical asymptotes. And I think I'm going to do that on a whiteboard. Give me 1 second. We would need to factor the numerator and the denominator. So I will start by factoring the numerator and the denominator. So that'll be x, take out a GCF of x, and take out a GCF of x here, and you get x squared minus 1. Those would cancel out. So to find our vertical asymptotes, I would need to set the denominator x squared minus 1 equal to 0. And you could factor that as a difference of squares, x plus 1, x minus 1, or you could take square roots. Remember, when you're taking square root of x squared, you put a plus or minus. So my vertical asymptotes, I would have 2. One at x equals positive 1, one at x equals negative 1. And if we look at our graph, here it is, negative 1, positive 1. Okay, simple as that. Now, a horizontal asymptote. Horizontal asymptotes are like vertical asymptotes. The graph approaches them but never touches them, but they're horizontal lines. And this definition you can read for yourself in the lecture notes that I attach. But we have some rules, and there are a whole bunch of rules, and you can read those later. But I've summarized them here. So there are 3 cases when you are looking at the numerator and the denominator. You're going to look at their degrees. If the degree is the same, the horizontal asymptote has the equation of a horizontal line, y equals, and y is equal to the quotient of the leading coefficients. So you just divide the leading coefficients if the degrees are the same. If we were in class, I would explain why this works, but we're not. If the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is y equals 0. And if your degree of your numerator is bigger than your degree of your denominator, then you just don't have a horizontal asymptote. Okay, there is no horizontal asymptote. So let's go back to our example. We look at this one, and all we're interested in for horizontal asymptotes is the degree. The degree is the same. What did our rules say about when the degree is the same? Our rule says if the degree is the same, then our horizontal asymptote is y equals, and you divide the numerator by the denominator. So that would be 6/9. Or when we reduce that, y equals 2/3 is the horizontal asymptote. Simple as that. Okay, so now we're going to look at an example, and we're going to find the vertical and the horizontal asymptotes. I'm going to have to write this one on paper. So vertical asymptotes, we look at the denominator. Nothing cancels out with the numerator. So what makes the denominator 0? A -3 would make this 0. So our vertical asymptote is x equals -3. If we were graphing this off to the side, I would go to -3 and put my vertical asymptote. Horizontal asymptote, you're supposed to look at the degree of the numerator versus the degree of the denominator. These both have an understood 1 for their degree, so we just divide the coefficients. 2 divided by this understood 1 right here, there's an understood 1 there. 2 divided by that understood 1 is 2. So our horizontal asymptote is y equals 2. And if we wanted to get a good graph of this, then we would make a little table like so. And we would plug in numbers. Like if you plug in -6, you're going to get 2 times -6 over -6 plus 3. So -12 over -3 is 4. -6, 4. So there's -3, -4, -5, -6. Why did I pick -6? Because I've worked this problem out already. But why would you pick -6? You would probably start with values of x that are close to the vertical asymptote. So like -4, -5, -6, and then -2, -1, 0. Those are the kind that I might pick. But then I look at, say, -5, and that gives me a 5. So -5 gives me a 5. 1, 2, 3, 4, 5. Okay, so I messed up on the first one. I plotted it too high. And then if I look at -4, I get 8. So you can kind of see the piece here, and then you're going to have another piece over here. If I plug in a 0, I get 0. That was easy to plug in. If I plug in -1, what do I get? I actually haven't plugged that in. So it'd be -2 on top, 2 on bottom, -1. So -1, -1. And you can kind of see how the graph would go here. All right, moving on to the next problem. Oh, look, there's a whole table full of values already done up for you, and that graph looks pretty close to what I did over here. You can do this, guys. I believe in you. So then we have something called an oblique asymptote. Graphs can have one horizontal asymptote or no horizontal asymptotes. If they don't have a horizontal asymptote, then they can have an oblique asymptote. And it only happens when the degree of the numerator is 1 greater than the degree of the denominator, like this example right here. The degree of the numerator is 2, the degree of the denominator is 1. So it's a special case of that when the degree is greater in the numerator than the denominator. We don't have a horizontal asymptote, but if it's only 1 greater, we can have an oblique asymptote. So we're going to try to find all of the asymptotes here. You see this funky looking graph? So you can probably already look at it and go, oh, look, there's a vertical asymptote at -2. And we go over here and we look at -2, and sure enough, there's a vertical asymptote. I'm not good at drawing this line. But there's another like separation here. That's not the only separation. There's a weird slanted asymptote. Oblique asymptotes are called slant asymptotes. And so here's how we would find all of the asymptotes. We've already said that the vertical asymptote is what makes the denominator 0. Horizontal asymptote. Well, we look, the degree of the numerator is greater than the degree of the denominator. So there's not a horizontal asymptote. Oh, come on and focus. Okay, so to get this horizontal asymptote, we are going to divide 2x squared plus 3x minus 5 by x plus 2. You learned polynomial long division, at least in Algebra 2. So we start off with the 2x squared divided by x is 2x. And then you have to multiply. 2x times x is 2x squared. 2x times 2 is 4x. But when we're doing long division, we then subtract this. So 2x squared minus 2x squared is 0. And then 3x minus 4x is negative 1x. Bring down your minus 5. Now we're going to divide the negative 1x by the x. So negative 1x divided by x is negative 1. Negative 1 times x is negative 1x. And negative 1 times 2 is negative 2. And we subtract this. Get 0. Negative 5 minus negative 2 is negative 3. We can't do anything with this remainder down here. So our oblique asymptote is y equals 2x minus 1. If we go back and look at our graph, 2x minus 1 would be here, and we go up 2 over 1. We're down 2 over 1, and we can kind of see this graph right here. That line right there would be the oblique asymptote. These slides are just kind of a summary of what we've already talked about. Things you might want to know about asymptotes: the graph of a rational function never crosses the vertical asymptote, but it might cross a horizontal asymptote, but it doesn't have to cross the horizontal asymptote. It just might. But it never crosses a vertical asymptote, and it might cross a horizontal asymptote. Say hey, Waverly. Say hey. Just say hey to him. Oh, bless it. I know. Okay, so now we're going to kind of put it all together. When you get ready to graph a rational function, you are going to find the real zeros to help of the denominator to help you determine the domain. So basically, find the vertical asymptotes. Okay, then you're going to find the horizontal or oblique asymptote if there is one. Then you're going to find the zeros of the function. So those are going to be the x-intercepts, which are the zeros of the numerator. We got our vertical asymptote from the zero of the denominator. Our x-intercepts are going to be from zeros of the numerator. Then you're going to find your y-intercept by plugging in 0 for x. That's what this means. F of 0 means plug in 0 for x, and that'll give you the y-intercept. And then just make a table. That's what this last thing is saying. Make a table. So here's an example. Let me see if my paper is going to be good for me this time. And I am going to first have to factor this denominator. So when I factor this denominator, let's see, that'll be a negative 3 and a plus 1. All right, you could tic-tac-toe or slip and slide and divide or whatever it is you do, grouping, AC method to get that factored. Nothing cancels out in the numerator and denominator. None of them are the same. So I find my vertical asymptotes, that what values of x make this 0. So that'd be negative 1/2 and positive 3. Now we look at our horizontal asymptote. The degree of the numerator is an understood 1. The degree of the denominator is 2. Since the degree of the numerator is less than the degree of the denominator, 1 is less than 2, our horizontal asymptote is y equals 0. Nope. Now it comes back into focus. All right, so because we have a horizontal asymptote, we don't have an oblique asymptote. So now we're going to find the x-intercepts. That comes from zeros of the numerator only. What would make the numerator 0? Negative 3. So, negative 3, 0 is my x-intercept. My y-intercept. What happens if I plug in a 0 for every x? That'd be 0 plus 3 over 2 times 0 squared minus 5 times 0 minus 3. And we get 3 over negative 3 is 1. So my y-intercept is 0, 1. Then we would go to graph this. Okay, we'd have to graph all those things. I had a little board prepared. Here we go. Need my paper so I can tell what we're doing. The vertical asymptote at x equals negative 1/2. Oh, even dried out markers at home. And then a vertical asymptote at x equals 3. And an x-intercept of negative 3, 0. Negative 1, negative 2, negative 3. And a y-intercept of 0, 1. These are the things that we found when we were graphing. Now that does not tell me enough to get this graph. So I have to go in and make a table. I need to see what goes on at negative 1 and at negative 2. So I make a little table and I plug in negative 1 and negative 2. And then I need to see what goes on at 1 and 2. And over here I need to see what goes on at 4 and 5 and 6. So I would make a table and find these values, plugging them in to this function. And here's what we get when we do that. Okay, you see my asymptotes. You see my x-intercept, my y-intercept. Oops, I put my y-intercept at positive 1 and it was straight up negative 1. If we look back at my paper, see in class y'all could have stopped me. If we look back at my paper, 3 divided by negative 3 is negative 1. So 0, negative 1 should have been the y-intercept that we graphed. And I would have figured that out once I plugged my numbers into my table and the graph was looking all wonky. All right, here's some more that you can look through on your own. This video is getting kind of long, so you can look through these examples on your own. I do want to show you this one. The x-intercepts, it says that you have plus or minus 2.828. How do you get x-intercepts? You set this equal to 0. So 8 minus x squared equals 0. So that would be 8 equals x squared. And then you would take the square root. So that'd be plus or minus. Square root of 8 reduces to 2 square root of 2. And that's how you get two different x-intercepts. When you type this in the calculator, the decimal is going to be plus or minus 2.828. All right, the last thing we need to talk about is holes in a graph. So holes in a graph occur when something does cancel out in the numerator and denominator, like in this example. So I factor the denominator. Okay, what multiplies to negative 2 adds to negative 1, negative 2 and 1. And I see that these cancel out, leaving me with 1 over x plus 1. Well, I have a vertical asymptote only at x equals negative 1 because these canceled out. And my horizontal asymptote would be y equals 0 since the degree of the numerator is less than the degree of the denominator. But I have a hole, and here's how a hole works. So since these are what canceled out, there is a hole at x equals 2. And I take that x value of 2 and plug it in to my reduced function. So y will be 1 over 2 plus 1. So there is a hole at the point 2, 1, 3. Now, what does a hole look like on the graph? I'm glad you asked. It looks like this. There's just a hole. So your domain, if you're talking about this, you have to take into account the hole and the vertical asymptote. So Be careful that you don't forget about, in this case, the x minus 2 that canceled out in the denominator. We couldn't have a 2 or a negative 1. So our domain would be negative infinity to negative 1, union negative 1 to 2, union 2 to infinity. And that is finally the end. Good luck. Y'all, please email me with questions. Bye-bye.